Sorry.
I'm one of several organizers for the seminar. So today for the first seminar for the semester, Camryn Undershute will be giving a talk on introduction to quantum computing, and I think specifically some extra parts about superconducting qubits. And then the rest of the semester, I think she'll say a couple words about what we'll be talking about. So yeah, if there's any questions before we get started, I would be happy to take them, or if there's questions after, I'll probably plan on sticking around a little later today. Yeah, so
Camryn, for questions during the middle, do you want people to just raise their hand?
Yeah, just raise your hand or call out or whatever. Yeah, so like Joe said, I'm Camryn. I'm a grad student here in Johannes Pollinen's group. And so this is the first seminar for the semester for our quantum information and computing seminar. And I think I kind of just wanted to start by mentioning that quantum information science is a really broad field, and there's lots of reasons why one might be interested in quantum information science. So in particular, I'm interested in simulating open quantum systems with superconducting qubits. That's what my research involves. I'm an experimentalist, but I was wondering maybe if any other audience members wanted to point out why they, or mention why they were interested in quantum information science.
There's really like any of the I see a lot of new faces, like what brought you here, what is interesting. Anyone, please? Yeah, I'm an undergrad electrical engineering major, and so this is probably where my work is going to be more headed for the quantum level. So it'd be interesting to get to know a bit more while I'm still in my undergrad.
Yeah, cool.
Thanks.
Yeah.
So my interest is in a closely related field, quantum metrology, precision measurements.
Are you
Yeah, I'm a grad student. Precision measurements.
cool?
Could you maybe say a few more sentences about quantum metrology? Sorry, quantum metrology is basically using quantum mechanics to perform measurements that would be really difficult or impossible to do otherwise. So, for example, you might want to measure something that's well below. That's great.
Anyone else? No, catch Camryn. Thanks.
I guess I have one. So I'm interested in studying photonic and photonic excitation at the fundamental level. So something that'll come up certainly this semester is how superconducting qubits specifically allow you to study these novel systems really at like the very fundamental. So that's something I'm interested in.
Yeah, so I hope we all think that there's, and thanks for sharing your answers. I hope there's lots of reasons why you might be interested in something like this. So I hope we'll cover topics that at least cover some of your interests. So just a little outline for the semester. Today is just an introductory talk. And then for the next 2 seminars, we're going to talk about superconducting qubits. And then for the next couple of seminars, we'll talk about QuIC. After that, we'll talk about quantum algorithms, and then we'll finish the semester with some special topics. So yeah, if something that you're interested in doesn't come up today, that doesn't mean it won't come up all semester. So make sure you come back for what you're interested in. Yeah, but if we want to talk about quantum information processing and an introduction to quantum computing, it makes sense to first just say a couple words about classical information processing, because we're going to draw a lot of analogies. So in classical information processing, we have a bit, so something that can be in one of 2 states, which we'll represent as a 1 or a 0, and then we can perform logical gates on these bits. And so here at the bottom, this is a truth table. A logical gate is defined by how it acts on the states of the bit. And so you can see this one will take an input of 0 and turn that into a 1, or an input of 1 and turn that into a 0. So this is a logical NOT gate, which makes a lot of sense. And there are also 2-bit gates. And so here is a schematic and a truth table for an AND gate, which does exactly what you'd expect. It outputs a 1 only if both inputs are a 1, and then an OR gate here on the other side. And you can generalize this to bigger circuits with more logical gates. So here's many logical gates strung together. And you can similarly generalize this to having many bits as your input and maybe even many bits as your output. And so now when we go to quantum information processing, sorry, some things might have moved around. So sorry about that if words are cut off. But yeah, when we go to quantum information processing, instead of a bit, it's a qubit. So this is, again, a 2-state system that follows instead the laws of quantum mechanics. So it could be in the state 1 or 0 or some linear combination of the two. And we usually use ket notation like this on the left, or vector notation. So this is the state vector here on the right. And this vector has a normalization, so its length is 1. And a nice way to represent this is with the block sphere. So any valid qubit state is one that lies on this block sphere. Ooh, sorry, this is really rough. I don't know what happened when I switched this over, but something does not look right.
If you go back to the, like, if you go out of presenter mode, does it fix itself?
No.
Was this uploaded from like PowerPoint or something?
No, I did make this in Google Slides.
Oh, it looks like the rest of them.
It's just,
Maybe just move around. Maybe just like give a presentation like this, you know, with that around scale.
sure.
But it's pretty brief.
Yeah.
Yeah. So I think what I want to say here is that when we write a vector like this, in ket notation, that's using the states that lie along the z-axis as our basis. But that was just kind of an arbitrary choice. And we could have similarly chose the states along the x-axis, which in terms of the ones that lie along the z-axis are written like this, the plus and minus states, or the plus and minus I states, which we can, again, parameterize like this. And when we measure the qubit, so here, when we measure the qubit, you have to pick some measurement basis. And this is an arbitrary choice, but that will be your computational basis. And so when you perform a measurement, you'll just measure where the qubit state lies in that basis. So you can't measure the state as a whole. And generally, we choose the states that lie along the z-axis as our measurement basis. And so this is fundamentally a probabilistic measurement instead of a deterministic measurement, like it would be with a classical bit. So for example, if you wanted to measure a qubit that was in this state, the state we call the 1 state, you could perform a measurement in the z basis, and you'd see that it's in the 1 state, and you can repeat this many times, and you'll always see that it's in the 1 state, as long as your measurement protocol doesn't have any errors. And so you can reconstruct with statistics your state to see it was in the 1 state. If the qubit instead was in the plus state, for example, you can perform a measurement and find, for example, it's in the 1 state, repeat it, maybe you'll find it's in the 0 state, and repeat this many times to get the statistics to reconstruct some other state. And so now that we know what our qubits look like, what do our gates look like? So here it was an example of what a single bit gate looked like. Now this is a single qubit gate. So you can see you start with 1 qubit, and then 2 gates are performed on the qubit. And then at the end of the logical sequence, a measurement is performed where you have to collapse the state. And this is similar with multi-qubits. And so here you have 2 qubits. There's a single qubit gate, a 2 qubit gate, and then you measure the state of each respective qubit. But what actually are these single qubit gates? And so the gates are linear operators. So they act like this. And mathematically, so mathematically, this is a U gate acting on the psi state. And they're linear. They're also unitary. So if you start out in some state psi that's normalized, so its length is 1, then when you act on it with one of your logical gates, the resulting state psi prime will also have length 1. And so these actually correspond to rotations on the Bloch sphere. And like before, we defined our classical gates by how they acted on our states. We can do the same. So you can consider a quantum gate that acts on your basis states like this, kind of similar to our NOT gate. And because we can write our qubit state in terms of kets or as a state vector, it makes sense to write our quantum gate as a matrix. So we can use our tools of linear algebra. And so this is a representation of this gate. And we can double check that it acts on our states the way we would expect it to. So we defined it as acting on the 0 state, brings us to the 1 state. And here, if you work out this matrix multiplication, you get back the 1 state after you act on it with this gate. And so that was actually a rotation about the x-axis on the Bloch sphere. And all of the Pauli matrices are actually some of our quantum gates. And so the Pauli Y matrix would correspond to a rotation about the y-axis. And similarly, the Pauli Z matrix would correspond to a rotation about the z-axis. And just there's 2 other important single qubit gates that come up really often, so I wanted to mention them. There's the identity gate, which does kind of what you would expect it to do. It leaves the qubit in the state that it was in. And then there's also the Hadamard gate, which is really important because it takes you from either the 0 or 1 state, and it brings you to the horizon of the Bloch sphere. So it puts you into a superposition state there. And so now we can talk about what would happen if instead we have 2 qubits in our system. And so now we can represent the state as a 4x1 vector. So here A00 is the amplitude that corresponds to the probability of finding the qubit or finding both qubits in your system in the grounds or in the 0 state. And similarly, 0, 1, this amplitude corresponds to the probability of finding 1 qubit in the 0 state and the other qubit in the 1 state. And this state vector has the same constraints as we had before, where it should be normalized for it to be a valid state vector. It has to be normalized to length 1. And our gates will also preserve the length of this state vector. So to start thinking about how we can apply gates to this 2 qubit system, we can consider how we would write, how we would treat the system when we want to apply the Pauli X gate to just one of the qubits. And so we'll also need to use our identity gate here because leaving a qubit in the same state is equivalent to applying the identity gate. And so we're going to need to take the tensor product of these 2 matrices. And so if you take the tensor product, it looks like this. And when you act on the 4x1 state vector with this matrix, you'll get the first qubit, the qubit we wanted to have had a Pauli X gate applied to it. Yeah.
Could I ask a question about the products?
Yeah.
This slide? So this certainly confused me for a while when I was learning about it. I was wondering if you could give some insight as to why you calculate the tensor product that way. So you sort of insert B into each entry of the matrix A. Like, do you have any insight as to like why we do it this way when we combine operations?
Because the math works out like that, and it takes you from so if A lives in the Hilbert space of one of the qubits and B lives in the Hilbert space of the other qubit, then the way you kind of combine these together brings you to the Hilbert space of the 2 qubit system as a whole. Yeah, do you have what helped you?
Yeah, so I guess, I mean, because it is sort of weird when you look at it, I think, you sort of combine them, it also sort of works out to where the way you order, like in the binary, the 0010, sorry, 00011011, the way you do this, if you only have, a tensor product state, this is sort of how you have to do it so that B only acts on the second system.
Yeah.
A only acts on the first system.
Yeah.
So if you're kind of curious, you can work that out. So if you have a tensor product in two states, this is how you do it so that A only acts on system one, B only acts on system two. Yeah. Not super illuminating, but.
She said it's like a tensor maps of vector space, right? And so essentially, when you take a tensor product, you're mapping the two qubits to the double Hilbert space, right? So I actually like what she said, like combined variables. It's like do the tensor.
Cool. And something about the tensor product will come up again. So thanks for your question and comments. Yeah, and so now what would an actual 2-qubit gate look like? So an example of a 2-qubit gate is the C0 gate. Schematically, that looks like this. So here you can see when the second qubit is in the excited state. So you could look at this line of the truth table, for example, the gate will flip the state of the first qubit. And so we'd call Q1 the control qubit and Q0 the target qubit. And you can write this out like this matrix. And if you consider how it acts on a 2-qubit state vector, you can see that it swaps these probability amplitudes. This comes up really often in conjunction with a Hadamard gate. And so if you remember from before, our Hadamard gate was the gate that takes you from one of the poles of the Bloch sphere to the equator. And so you can consider what would happen in this logic circuit. And so initially we can say that we'll say that both of our qubits are in the ground state, or sorry, in their 0-0 state. And so that state vector would look like this. And then we apply our Hadamard gate to the first qubit only. And so that puts us into this state. And then when we apply our C0 gate, we get taken into this state here, which you might recognize as a Bell state or a maximally entangled state. And so this is how you can generate entanglement between two individual qubits. And yeah, so this is where the tensor product comes up again. You say that a state is entangled if you can't write it as the tensor product between two states. So this state is an entangled state because you can't do this decomposition into two individual qubit states. Yeah. And so now that we've talked about, oh, sorry.
Is there a good mental picture of that? Block spheres that are coupled?
In a Bloch sphere representation, this kind of falls apart because if you think about this state, you have an equal probability to measure the first qubit in the 0 state and the 1 state, and similarly with the other one, yet they're correlated. And so they would almost be like points. Yeah, so here you could, at the top point, you could think about both qubits pointing completely up. And then at the green one of the qubits is still pointing up while the other one is pointing out to the equator. But then it's when you get to this point at the end that the Bloch sphere picture kind of falls apart.
So if a 2-qubit state is separable, meaning like the green box, you can factor out 0. Then you can think of like 2 Bloch spheres. When you get to these entangled states, it's a little trickier. So the mathematical representation, like the Bloch spheres can be represent some qubit states, but for entangled qubit states, the mathematical picture is now, I think, like, I think it's the surface of the forest or something, which gets to be so complicated it's not useful anymore. So
there is a tool, it's just. Angled states are a little tricky. I also say it's for those who are curious and haven't done it before, it is a interesting exercise to try to show that you can't write the Bell state as a tensor product of states. In case you're curious. Also, people have tried to represent tangled states in the sphere. I think IBM tried to use sphere to some degree of success, but definitely not the same. That's interesting. The block sphere is very, I find it quite intuitive.
It all
You
falls
make it
apart.
into the tool, difficult to understand, it's not.
And this also kind of shows how why these states are interesting, because they're these states that you really can't achieve with classical computation. Oh, yeah. So there's the strongest correlation between the two qubits. They have the strongest correlations. So if you're in the 0, 0 state, if you perform a measurement on one qubit and find that it's in the 0 state, you know that the other qubit will be in the 0 state. Yeah. Yeah, that also, so yeah, I guess there's a family of maximally entangled states. So if instead here you had in the first ket like 0, 1, and then in the other ket 1, 0, that would be another maximally entangled state. Yeah.
Maybe for reference, just when you say maximally entangled, compared to what?
So like at this point, say you had this state and you did a measurement on your first qubit and it was in the 0 state. You really can't say anything about your other qubit at that point. You don't know. It could be in the 0 state. It also could be in the 1 state. And then you can be in a situation kind of between these two where there are some correlations between your qubits, but they're not as strong. Like there could be some other small component of the 0, 1 state here, for example. So if you measured your first qubit in the 0 state, you'd say, well, my other qubit's probably in the 0 state, but because you have this other component, it could be in the 1 state too.
Well, I was gonna say, I don't know if you remember like what I was talking about last term with the mixed states, but that's kind of what it's like. When I was kind of researching about that, people were trying to quantify entanglement, and it's actually like not a true thing. Like, I don't know if it's necessarily to say it. One thing that somebody proposed was actually using Bell states. It's like the measurement of entanglement. It's like third unit. So it's really not like a thing to be like, oh, it's like, but I would think that maybe it's like a mixed density matrix, mixed state density.
Yeah, this topic is very deep, so people are very excited and enthusiastic about it, but one of the organizers know, and we can try to make it happen. But I think Camryn's doing a great job of giving a short summary at the time. Yeah.
Are there any other questions at this point?
Question, just to close up the discussion. So there are indeed various metrics of how to quantify entanglement, and one of them, for example, was not mentioned. One can calculate this quantity for two qubit systems which are entangled. And if you calculate this quantity, you will see that this quantity is maximum when you have a Bell state. And for the green state, which is shown there, this quantity is equal to 0. And that's how you quantify the entanglement. So the Bell state is maximum entanglement just by calculating this kind of thing.
Maybe
No,
for sake of time, sticklers at the end.
Yeah, so moving on. Bits really, all we said was that classical bits had to be something that has 2 states. So great kind of pictures in your head are like a light switch, a 1 and 0, or a coin where it's heads or tails. There's also some really interesting historical examples of things that people tried to use as bits for the purposes of computation. But the modern day choice is integrated circuits. And so similarly for qubits, there's a handful of different things that we can use. Some common examples are defect center in diamonds, quantum dots, You could use polarization states of light for photonic qubits. You could use trapped ions. There's also some more exotic options like electrons floating above the surface of helium. And then also another common one, superconducting circuits. And so now that we've talked about all the pieces separately, can I show you a picture of like a great working modern day quantum computer? Like where are we at in trying to reach our goal of universal fault tolerant quantum computing? And to make it to give you the answer right away, we are not very close to our goal. So a lot of people will use the term NISQ era, so noisy intermediate scale quantum computing. So this means that these are systems limited to 50 to hundreds maybe of qubits, but the qubits decohere and the gates are noisy. So we cannot provide or perform reliable computation with these systems. There is quantum annealing and quantum simulation that are commercially available now, but even those are pretty, I think it's not clear if they provide the advantage that quantum computing at some point promised. Yeah, so on the quantum computing forefront are two companies, IBM and Google, that both are really pushing on the edge of what we can achieve with quantum computing. And so Google, I think a year or two ago, announced that they achieved quantum supremacy with a superconducting qubit processor. Whether or not they did, I think some people, there's speculation. And this was with 53 physical qubits. And then IBM recently announced their newest processor that had 400 or more than 400 physical qubits, and have announced plans for one with more than 1,000 physical qubits in the coming year. And kind of at this point, what I wanted to emphasize is that at the forefront of quantum computing research and industry is superconducting circuits for the qubits. And so that'll take me to my second part of this introduction, where I'm just going to focus on superconducting qubits. Does anybody else? Yeah.
So let's ask the number of qubits will keep the power of or how does it work? Would there be like limitations if you add more?
Yeah, so at this point, it's hard because when you add more qubits, you add more possible places where noise can be introduced to your system. So you can add more qubits, but I think there's very few systems where they've shown that adding more qubits gives them a system that is better at actual computation. Yeah, really good question. Sorry, I kind of glazed over that. I wasn't expecting as many new faces today, to be completely honest. So yeah, quantum supremacy, it's a jargony word that's thrown around a lot. I think what it's supposed to mean is that a quantum computer can compute something that a classical computer realistically wouldn't be able to. So maybe it's a problem that should take a classical computer like thousands and thousands of years. Yeah.
And I think to comment on some of the controversy you alluded to after Google sort of did this paper, I mean, the theme in this kind of research is the folks on the classical end that try very hard to show, no, actually, you can do this. Sometimes they come up with new algorithms, sometimes they just use an existing method. But I think slowly people, this was in 2019, people whittled away at the time. I think it's the original paper, it was hundreds or thousands of years, like 10,000 years. People whittled that away. It's still like,
I think
takes
like
a
2
day.
weeks.
So it takes like a day for takes. Okay, we do. I think so. Anyway, one point being, there's sort of this downward trend, and it's always this complicated thing, and people are still on the hunt for like a very definitive case, I guess.
So one more thing on that. You asked a question about is adding more qubits always better? And something that is tricky with these that Camryn mentioned is if you have this large scale quantum processor, the power is that you can get these qubits to talk to each other. And create states. And something a lot of these large scale processors struggle with is if you have one qubit in the middle, which is bad or whatever, then it breaks your processor into like two separate parts. So now you're say 400 qubit to 200 qubit processor that can't actually achieve it. This is one of these things. Scale.
Was there, yeah.
So, you know that, it does go there. You have like items, those days, the gates. Does it change the, speed of, calculation that? That's the same for, the gate, you have like non-entry states.
Yeah, so I think that is actually one of the, so to preface this, I don't know, I know next to nothing about quantum algorithms. But that is one of the things that's inherently powerful about quantum computing, because if you, a qubit doesn't have to be in the like a 1 state or a 0 state, it can be in some superposition state. And so already that qubit holds more information than a classical bit does. So that,
Not more than 2 states, and your final calculation is for the states.
oh, like if you used many states.
Just one, you have one qubit, but
Yeah.
not more than.
Yeah, so I think,
Like a qubit,
What?
like a qubit, like a single qubit where you access
Yeah,
more than.
qubits, not more than.
So it's, I think it sounds like you knew something, you know something about the classical side of the story, like. One could have had, instead of bits, they could have had 4-state systems or something like this. And then you ask, why didn't people do that? And the answer is you throw a billion of them together, you still get 2 to the billion states instead of 4 to the billion states. Well, the scaling is still exponential, so why not just use two levels? It's easier to control each individual system. It's the same. So it's sort of the same story with quantum computing. People expect in the long term of history, if you can kind of manipulate lots and lots of qubits, or we'll say single systems, why not just make them small systems? You still have the exponential behavior. That's one answer. But people do today look at using as their baseline multiple level single systems. And that is an accurate research. On the hardware side, it's a different story. That's the way to do things. But from a theoretical perspective, you say it's all exponential anyway as you increase the number of systems. So
yeah, is another way to say this that you would get more like bang for your buck, so to speak, by just adding another qubit or adding another bit
much better than I said.
rather than adding another. So you get more computational power by adding another bit to the system or adding another qubit to the system, rather than going from a 2-level system to a 3-level system. Does that make any sense?
I don't know how much, right? But so my perception is that the advantage of qubits or bits is that instead of reading the bits either like 0 or 1, you read the qubits and it's in this relation. So it kind of helps you to do some sort of transform on that and exploit more data than just finding out there's like either 0 or 1. You can exploit more data. So my understanding, it should be like different from the classical gates in terms of adding more states.
I kind of see, yeah, are you saying it's almost as if you had a classical system but added more instead of a bit? It was like a 3-level system or a 4-level system, like you get computational power in that way?
Yeah, but I think it should be different. Like I know for classical computing, it wouldn't change that much.
Yeah.
That's pretty same as you're measuring superposition, say of computing, it should change a lot, I guess.
Yeah, I don't, as far as I know, I think it holds with qubits too, that you get more bang for your buck by adding another qubit to the system.
Maybe we could talk after the seminar.
Yeah,
It sounds really interesting.
Sorry.
No, this is great.
thank you. Did anybody else have any questions at this point? Okay. So a couple minutes ago, I said that superconducting qubits specifically, or superconducting circuits are at the forefront of qubit industry or quantum computing industry. And why is that so? So a couple of things. Because of modern fab techniques, we can design and tune the parameters for these circuits. Like they're all pre-designed before you go out and make them. And they're also very reproducible, especially compared to something like maybe defect centers and diamonds, where you hope that you get the same conditions from sample to sample, but that might not be true. In addition, they're scalable-ish, definitely more scalable, so they take up less space. You can add more qubits together compared to some other qubit platforms. And they also have fast gate times relative to decoherence times. That's a really big one. If your qubit is going to decohere or lose its information before you can perform some logical gate, it's not really a useful qubit. And they also usually are designed to have gigahertz-ish frequencies. So if you stick it in a dilution fridge, you'll cool it naturally into its ground state. But what actually is a superconducting circuit as a qubit? So if we're going to be talking about circuits, one of the most fundamental circuits that has a resonance is the LC oscillator that we all know and love. And so in this LC oscillator, the energy is going to be oscillating back and forth from the inductor to the capacitor. And we want to write down the Hamiltonian for this circuit. And so we're going to arbitrarily choose to associate the kinetic energy with the electrical energy and the potential energy of a Lagrangian with the magnetic energy. And so we can write this integral for the instantaneous energy in any of the circuit elements. And then we'll define a generalized coordinate, that is the flux, with this integral. And then we can write down the kinetic and potential energy using these equations that we know hold for circuits as these. And then we end up with a Lagrangian like this. And I don't know how familiar everyone is with classical mechanics, but this looks a lot like your particle in a potential trap. So from here, we can do, if we still want to get the Hamiltonian, so we can do a Legendre transformation to get the conjugate momenta, which in this case is the charge Q. And then we can write down the Hamiltonian like this. And again, sorry, I think I said potential in a 1D trap. I'm thinking ahead. This should look a lot like a mass on a spring. So here, if you replace C with the mass and L with the spring constant, you would get mass on the spring that we all know and love. And so if we, we can define the reduced flux and the reduced charge up here. And then we can write down the quantum mechanical Hamiltonian like this. And so phi naught is the flux quanta of the inductance, and EC is the capacitive charging energy in the capacitor, and EL is the inductive energy. And then we end up with this Hamiltonian. Again, really similar to your particle in a 1D trap now. And that has these harmonic energy levels. And so this is great, but at some point we have to pick two states and say these are going to be our qubit states. And so here you could say, okay, I'll pick the lowest two of these states. But then when you try to experimentally address them, so say you start in the lowest state and send energy into your system at this energy difference, you'll just go up this ladder indefinitely. So this won't work. We need to have some difference in energy level spacing so that we can pick and isolate just 2 of these levels. And to do this, we'll introduce a nonlinearity in the circuit. And so we do this by introducing or putting a Josephson junction in place of the inductance. And so physically, this is because our circuit is superconducting, this is just a little insulator between 2 superconducting arms of the circuit. And so electrons that are paired into Cooper pairs in the superconductor have some tunneling probability to go through the insulator in the Josephson junction. And so with our Josephson equations for the current through the Josephson junction and for the potential across it, we can redefine that Hamiltonian we had on the previous slide, and now it'll look like this. And so here you get a potential landscape that looks like this now. And the important part is that we have some anharmonicity. And so the difference between the 0 and 1 state is different than the difference between the 1 and the 2 states. And so we can pick the lowest and then the first excited energy state as our computational subspace. Yeah, so without the Josephson junction, the solutions to the eigenstates of the Hamiltonian describing this circuit are these dashed lines, like these are the energy eigenstates. Yeah, and so say your system started in the ground state and you wanted to put it up into the first excited state, you would send in the energy difference of those 2 levels, but that's the same as the energy difference between the second and the first excited state level. So then if you're just shining a laser at your system that has that perfect amount of energy, it will take you from the ground state to the first excited state, but then the first excited state to the second excited state, and so forth. But for a qubit, we really just want like a 2-state system. Yeah. Yeah. And here? Yeah, sorry, I kind of went a little quickly through this. This is the reduced charge. So this is the charge on the capacitor plates here, I think. Q is the charge on the capacitor plates.
So N is, well, I mean, divided by 2, but I guess it's sort of the number of electrons on the capacitor.
Yeah. Yeah. Oh, yeah. So here we have a quadratic part. So this is the part that we've associated with like potential energy in our Hamiltonian, and it's a quadratic term in phi. But when we introduce the Josephson junction, we instead get this cosine term in phi. And so if you see the red dashed line in the background here, that was the potential landscape we had before, but now we have this potential landscape that has some curvature to it. And so our energy eigenstates aren't linearly spaced anymore.
There's still multiple or just?
Yeah, there's still multiple, but do you see here how it's like denoted omega 0,1 and omega 1,2? Yeah. Those aren't equal to each other. So now if your system's in the ground state and you shine a laser at your system that has just the right amount of energy, like the frequency matches omega 0,1, then it'll take you from the ground state to the first excited state, but you'd stay there. You won't go up any further. So we can kind of treat it like it's a quasi 2-state system now. Is there any other questions?
Just so you know, we have about 13 minutes left.
Okay,
So
perfect.
whatever you want to do.
Yeah, thanks. I think I'm close to all that I wanted to talk about. Yeah, and so now that we've introduced this nonlinearity, we get these anharmonically spaced levels. And this is also why oftentimes superconducting circuits are referred to as artificial atoms, because they have these atomic-like energy spectra. And also why they are very useful in experiment, because the energy spacing and other parameters are things that we can set when we're designing them. And with this Hamiltonian, the things that we can set when we're designing a superconducting circuit are EC and EJ. And so what do the energy eigenvalues look like for different values of EC and EJ? Well, you can see them plotted here. So the black is the lowest energy eigenvalue, red is next, or is the first excited state, blue is the second excited state, and the x-axis here is variations in N. And how I said N was the number of charges, the reduced charge number. You can see that for low ratios of EJ and EC, these energy eigenvalues are going to change quite a bit as you have small variations in N. And this was very problematic in experiment because you could have little noisy charges everywhere that caused your qubit to change energy spacing. And so if you move to these large ratios of EJ over EC, you get these flat lines. And so they're insensitive to charge noise. And that's what we call, that's what we call the transmon qubit. It's this qubit when we live in a regime where EJ over EC is really large. And to just add one more piece to this, if we replace our single Josephson junction with a squid loop instead, so this is a loop with 2 Josephson junctions, now we can tune the frequency of our qubit. So we can change the energy level spacing with an externally applied magnetic flux. And so that's a bit about the transmon qubit. All the other superconducting circuit qubits are just variations of these. So with your Josephson junction, your inductor, and your capacitor, you can pick any combination, put it together, and it's some qubit. There's some really exotic ones out there, but the transmon is the most common. This was all I wanted to talk about this time, but next time we're going to keep talking about superconducting qubits, CQED, and Schrodinger cat states, and eventually we'll be talking about this experiment. Does anybody have any other questions?
Questions for?
Yeah.
Third one, like, like, I guess, like, how do rule of these, like, quantum theory, apply it to be could be longer?
Ooh, well, I think by definition, entanglement isn't supposed to be a local phenomena. Like it's the whole spooky at a distance or action at a distance kind of phenomena. It doesn't violate relativity because you can't actually send any information, but it's a non-local phenomena. I'm not sure if that answered your question.
But yeah, like, I guess quantum theory. And when I say local and quantum, they're in any model. Yeah, so they're talking about causality, not about, because it's a quantum theory, so it has quantum. Another way you can put it, you can start with 2 uncorrelated systems, unentangled, and then they'll say correlated. 2 uncorrelated systems. You interact them locally because all your interactions always have locality and then you set them very far apart. Now they're correlated with each other. They're no longer interacting with each other. You know that exactly analogous situation in classical probability. You have 2 systems interacting far apart. Their properties are important, but they're just people are still spooked out by the non-locality of quantum, but they're 2 different.
Yeah.
What's it mean to measuring different bases for a super?
So yeah, we choose. Okay. So when you pick something as your computational basis, it makes sense to measure in that basis. But instead, you could have picked like the basis along the x-axis as your computational basis. But when you measure it, because the measurement doesn't commute, it will wreck other parts of the qubit state. And so, for example, when you have this state here, that lies at the equator, when you do a measurement in the Z basis, you're going to get that it's in the 1 or the 0 state. And so that's knocked your qubit off of its position on the equator to either the 1 or the 0 state.
But you're asking for super.
Specific. So it makes sense, like, okay, it's like ion, like a magnet,
Yeah,
right? Okay. I mean, there's these-
Yeah.
But for superconducting,
so
I've always been confused about that.
the Y and the Z basis are kind of weird because they don't have an energy difference, but you still could send in a pulse that in your visualization of the block sphere just rotates it to like projects it onto the Z axis and then measure the component in the Z axis. And whether or not you are going to measure whether you're going to rotate about X or Y to project Y or X onto the Z axis just corresponds to a different phase of a microwave tone you're sending into the system. I'm not sure if that's super satisfactory.
I think the last thing you said, like, answered
I think
the
it-
answer.
you have to rotate, but you're measuring like, right, or what exactly?
A microwave tone. So that the change in frequency and phase of a microwave tone you
So
send
in
into your
the
system.
superconducting qubit, we have a resonator as a part of the system which reads the qubit state. So you cannot just measure just by, so yeah, you need to have some instrument to measure the state. And that measurement, and that device is called the resonator. And you just measure the resonator state. And it turns out that the resonator, the interaction of the resonator with the qubit, the Hamiltonian commutes with the qubit Hamiltonian. And that's how you define the state. Yeah.
So just the resonator just happens to be in T basis.
Yeah, because of the interaction. Yeah.
It's
Hamiltonian.
a consequence of how the qubit in the framework of certain quantum mechanics. There is other paradigms of superconducting circuitry where interaction is built in X basis. So those experiments, what they have to do is rotate their states to X basis and then bring up the. So that's where you're not comfortable with a resonator, rather which is a different. So the fact that for superconducting it just 3 dozen T basis is consequence of dynamics. It is unique to that.
It should be pointed out, this is not a weakness of the superconducting architecture. If you can measure in one basis, say the D basis, as you started looking into Camryn, you can do some arbitrary unitary rotation to that basis, and that's equivalent. So, yeah, if your architecture does not have built-in multiple different angles for your magnet, formally you don't do that. It's just as powerful.
Is there any other questions or? Yeah,
But I think that handle from.
oh, yeah, sorry. And this is something I could talk more about too next week. So on the x-axis of these plots, it's fluctuations in this parameter n. And then the black, red, and blue are the eigenenergy values of the Hamiltonian. And so on the top left, when you have these parameters EC and EJ set so that their ratio is very small, then the energy eigenvalues change a lot with small changes in n. Whereas when you have EJ over EC set to something very large, they're relatively flat. Yeah, so this is why we'd want to build a qubit with an EJ over EC that's relatively large so that the energy spacing won't change for small changes in n.
We want small. But you still want variation on it. Oh,
Yeah,
and what is called?
just a type of this superconducting qubit.
I think for sake of.
Yeah.
continue talking.
Yeah,
And as Camryn mentioned, she'll talk more about this, I think,
next week.
So let's give Camryn one more round of applause.
Thank you.
Yeah, we'll keep this going.